Alberto Carpinteri, professor to the University of Torino, Politecnico di Torino. And please come in. Correlation between nanomechanics instabilities, pH zeta phonons, and subatomic particle emissions, implications to geometry and electrophysics. Thanks. Aspetta che sai come fa? Ma non so qual è il bottone per passare. Assia abilita la condivisione. E no, qui dice l'organizzatore si è abilitato la condivisione dello schermo. Secondo è questo, vero? Poi un po' più grande, più grande. Le freccette c'è anche sotto praticamente per andare avanti. Ecco, posso fare così. No, non funziona. Una cosa sì, pure freccetto che è un po' dura la freggetta, il tasto un po'. Ok, sì. Ok. Sopra? Sì, no, visto. Ok.
Good morning to everybody. The title is very general, but I can simplify the title saying that my speech, and I will be short about some subjects and more deep for others, could be synthesized in this following way. We have a stronger correlation between stability phenomena at the nanoscale, typically fracture for solids and cavitation or turbulence for fluids. Then we have the second point is related to particle or subatomic particle emissions, typically neutrons and or alpha particles. And lastly, the third point is very important, in my opinion, chemical balances. No? Chemical, you can say, we have stoichiometric balances before and after the test. So these three situations are in some way correlated and can intervene in different phenomenologies. Okay, in my previous speeches, especially 2 years ago at ICCF, I presented my experiments in the laboratory about crashing of rocks, especially, and then also the topic of seismicity and the evolution of elements in the Earth. This is very important, but several people think they are not in some way connected with electrolysis of cold fusion. But if we consider the three repeatable phenomena that I considered, So that I recall to you, so fracture, you can say, particle emission and chemical balances, we have strong, very strong analysis. So just to remember, recall you what I said in the previous presentations. We began in 2008 with 4 specimens, 2 of Carrara marble and 2 of granite. We took them to failure by compression, of course. We obtained this kind of ruptures, no? And we reported load versus time diagrams, which is not interesting for this community. Is much more interesting to see if there is some emission, but from Carrara marble we never had 1 neutron more in excess with respect to the background. Instead, with granite and other materials, we had always neutron emissions. For example, in this case was the first that we published. We have emission of between 7 and 8 times the background. With other materials, for example, basalt, which is the second one from the left, we had up to 100 times the background. With the magnetite, which is full of iron, or is an oxide of iron, practically speaking, only one mineral in the magnetic, we had up to 1,000 times the background. So we have Dr. Borla is a very clever specialist in Italy about the measurement of neutrons or weak fluxes of neutrons or environment neutrons. And he and the community was very impressed at the beginning by this very strong emissions due to macroscopical mechanical phenomena. Even if we have to say that the ultimate cause is not macroscopic, but nanoscopic. We have the conditions to have a nanoscopic instability. Then, from the chemical point of view, I skip some details, of course. We had this sophisticated chemical test with the best specialists in my university. This is the statistic if you are interested, but I have no time to want only to remind you that we had very important balances in terms of important ponderal terms of stoichiometry. In fact, what is disappearing in iron is appearing as aluminum in phengite, because granite has 2 iron minerals, phengite and biotite. In phengite, we have a balance -2 + 2 between iron and aluminum. In biotite, the situation is a little more complex. We have -3 in iron, you see. Biotite is richer in iron, you see 21% amount of iron. But what is interesting is the difference is -3, the iron, +3. But not only aluminum, this time we have to consider also magnesium and silicon, which are the 2 elements adjacent to aluminum and the layer table. Also, marble is very interesting because we did not obtain neutrons. We thought because marble is, we said at the beginning, marble is not sufficiently brittle, or in marble there is not iron, but this is not the reason, because if we see carefully the chemistry, we have -13% in calcium, very important like iron, I think, not less, calcium, magnesium, and oxygen. And we have a gain of 13% exactly, in this case it's exactly, of carbon. So chemistry before and after is very important, in my opinion. Just a brief sentence about Earth. two cycles in Earth during the life of our planet. There is the iron cycle, I call it the iron cycle. Better to say maybe depletion of iron or depletion of ferrous elements. They disappear, not completely of course, but 12%. You see that the iron from basaltic, the Earth at the beginning was basaltic like the Moon and Mars. Now is sialic, it means granitic. So much less iron, from 15% to 4%. 4% is very few because it's very small quantity, because you have to think that aluminum from 4, it's now 8%. So big changes that usually are explained by migration theories, by specialists in geology. Migration in the solids is difficult to think about migrations. But what is astonishing, in my opinion, is perfect balance between the depletion of iron and nickel and the gain in aluminum, silicon, and carbon. They are exactly the same, 12%, minus 12%, and plus 12%. The same for alkaline ferrous and alkaline, plus oxygen. In this case, we have 8.7. Is the percentage of matter that is transforming and transmuting. In our hypothesis, of course, transmutation, because you understand that the migration is not implying at all any balance. Migration doesn't imply balance. This is a basic logic, not the nuclear physics. Anyway, this is just a rapid. Now, why all these things are interesting in general, I think, but why are also interesting for our phenomena, at least the phenomena interesting in this community, for example, cold fusion in electrolysis. So I thought about this some years later, from 2008, we were at the time of 2012, I decided to begin with the help of many different people, from different disciplines, to perform electrolysis experiments. Then we had the preliminary phase, very interesting, because at the beginning we used different materials, for example, iron, chrome, and cobalt chrome electrodes. We published also something, probably some of you have seen this publication. Then we considered the palladium and nickel as anode in the cathode. This is the cell with these two different important elements, which are the most important elements for the absorption of hydrogen. You see on the right the geometry of the two electrodes. You have to consider that we always used a solution of potassium carbonate. And another thing very important, we considered the very important phenomenon of hydrogen embrittlement of these electrodes. I can tell you that the mechanical behavior after this phenomenon of these materials is very, very similar to the behavior of rocks. In other terms, they become very brittle, which is important, is a condition to have our phenomenon. And then, most importantly, in the next slides, I will show you the three phenomena: fracture or microcracking, neutron and alpha particle emissions, and lastly, the very important chemical balances. So, for example, this is one of the most interesting pictures, in my opinion, because this is a magnification of a mesocrack. We cannot say microcrack because it's long, its length is some millimeters, and the crack opening or width is about 40 microns. It is in the palladium longitudinally, in the palladium after 20 hours of electrolysis in palladium electrode. And you have to recall that even Storms, in his well-known book, says that we cannot have cold fusion if we have not microcrating or damage of electrodes. When I read it several years ago, I was impressed because at that time we had all this experience in fracture mechanics of rocks and so on. So I thought, why not to apply to this phenomenon, new phenomenon, because we have extensive microcrating the electrodes. Then we have emissions, very strong emissions, especially of neutrons. You see here the burst or peaks in neutrons, CPS, this is the rate of neutrons, and we have the background and then the peaks. This is the cumulative, maybe it's more significant or more easy to read. They are the cumulative with the cell off, cell on, no? Excuse me, cell on is the upper one and cell off. You see that there is a 30% about of increase when the cell is on, the electrolytic cell. This is about the neutrons. About the alpha particle, not the less interesting, because of course the emissions are less strong, but very interesting to compare cell off with cell on. You see, also in the rate is very visible to increase about twice, and also in the cumulative of alpha particle, the situation is objectively changing. And what about chemistry? Very, very interesting. Chemistry is the most interesting in my view, because we repeated the same experiments four times. And in the first experiment, we had only the radio at the beginning after 20 hours. 20 hours is a lot, much more than the incubation time. But it was significant. We were in some way safe or sure to have the results or have the best results. You see that the palladium always decreases about 30%, maybe in this case 28.7, I think, but other cases around 30%. Then we have always increasing oxygen, iron, other elements, potassium, magnesium, silicon, etc. Less important variation, and oxygen is very important. Why this distribution is repeatable 4 times the same distribution? So if you believe in this Length or anomalous fission, maybe very natural in my thought, but we say anomalous. In the way we have in this, I don't want to comment all the details, of course, but our major hypothesis was you cannot explain in a different way, I think. In some way, we consider a primary fission of palladium. And you may observe that the atomic number of palladium is 46, exactly 20 plus 26. So we can, of course, this hypothesis coming also from the very important cycles of iron and calcium. And calcium, which are the most important, in my opinion, elements in this dynamics of the Earth. So it was quite natural to think about that. The first primary fission and then secondary fissions. In this way, you can explain in a complete way the table. The only 2 discrepancies are that the iron is in this table is a little more. Theoretically, we should have 16.8, so 1.7 less. Why we have this oxygen in excess experimentally, and also potassium is 2 in this case, but is theoretically 1.5, so 0.5 more. So totally 2.2 is smaller, I think, this capacity. But we can explain this because you have not to forget that we have potassium carbonate. So they are, in my opinion, they are deposition of these 2 elements. I want to say potassium and oxygen. So we have a balance, a very, very good balance, I think. The balance is reported in this table, where we have the ponderal balance. Of course, in this case, we respect stoichiometric ratios, and this is corresponding to the table, the experimental table I showed you. So we repeated this kind of reasoning 4 times, quite exactly, so there is no need to say anything about test 2, 3, and 4. Just an additionally, I can say that as the total error, you can say 2.2 in the first, was repeated in some way, also in the other ones, not exactly, of course. The second was 5, was the worst. The third was 3.9%, and the last was the best, because it was 1.1% of discrepancy between theory or assumption, theoretical assumption, and experiments. So, in my opinion, is the only way to explain what is happening. Of course, I know that not all, but nearly all these fissions are endoenergetic. So this is the point to clarify. About the other things, I should not have doubts. But why we have energy from this phenomena? Because I'm not going to speak about it, but we have energy from this phenomena. Then, if I have time, some words about cavitation. I have some time. Yes, I think so. Yes, cavitation was a completely different experience, of course. Even if we have a strong analogy, I will show you. This is the setup, the global view of the setup. You see this. This is a hydrodynamic cavitation. No? Hydrodynamic cavitation means that we have a small circuit with water and a solution of iron chloride, and we produce through a cavitator, which is a specific tool, this cavitation phenomenon, which is a particular form of turbulence, because it means that the bubbles are imploding, no? Usually a very small bubble imploding is an extreme kind of turbulence in some way. This was in some way realized with this small circuit, but you can also imagine to enlarge the scale to have the same phenomenon with different scales. So it's impressive to think what we could do in the future. So this is the plant, the general view. And we have what we want to say before we go on, we have the same phenomenology. In some way, we have this kind of instability, bubble implosions. Then we have, also in this case, I do not read the graph, so unfortunately, we have neutron and alpha particle emission, even because the plant is made by polymeric materials. This is for 2 reasons. The first reason is to have no contamination. Only plexiglass or you can say polymeric materials, and the second reason is to have transparency to neutrons. The alpha particle is more difficult to think, but to neutrons we have transparency. You can say with of course if we have steel, it should be much different situation measuring these particles. Then we had, also in this case, we had the iron nearly disappears, and at the same time, aluminum increases its presence in the circuit, whereas at the beginning it was completely absent. Aluminum increases, but from zero. So we have this chemical it's not the balance in this case, but we have an exchange role between iron, which is disappearing, and the aluminum. And then, most importantly, the measure of the dimension of the bubble, because you have to understand that nano and macro bubble can emit energy, very significant amount of energy. When the bubble is bigger, even imploding, we have not this emission. So it was very important to construct you can say, the statistics of this bubble. And as the specialists know very well, we have a peak around 10 microns, which is much bigger, what is interesting for us. So when we collaborated with the firm, which is specialized in these measurements, and they were, when we asked to measure bubbles at the scale of nanometers, they were astonished because they say that usually it's not interesting. And we said that for us it's very interesting to know what happens at the nanoscale. So we found these bubbles. Of course, not there is a continuous line approximating it, but you see that for example, in this case, which was a particular case of a cavitator, we obtained up to the smallest bubble were 3 nanometers of the diameter, which is very, very lower than the usual measurements. So maybe the first time that was measured so small bubbles, at least according to what the specialists say. So the most important results up to now is that we had, by changing the cavitator, this means that to have a very big change in the number of nanobubbles, we have a constancy. The constancy is this average emitted energy per nanobubble implosion. And you see that this average is always around 34, at least appears to be around 34 millijoule, which is a lot of energy for a nanobubble. It's not the origin of this energy doesn't appear of a mechanical type. It appears to be another kind of energy. And we don't know, maybe nuclear, maybe, but I don't know exactly why so big this energy. Okay, if I have some minutes, I can say something about the final remarks, we can say. This is not a theory, only remarks about this. You see that we have 2 scales. There is a strict correlation between the velocity of the waves. At the left extreme, we have that the terahertz phonons are given by nanoscale mechanical instabilities. At the right extreme, the other side, you see that, as we said, as we know very well from seismicity, or seismicity, for earthquakes, we know that at the scale, we can say to the Earth vibration or oscillations corresponds the dimension of the faults. Faults are about kilometers scale, is the kilometer scale. Then we can also consider all the other subdivision of the scale, but I have no time. Of course, different instruments to measure these vibrations, from the human here up to the, because at that scale we have not electromagnetic or acoustical tools. We have to use the neutrons, in my opinion, and in fact, the left extreme in this case is represented by helium-3 neutron detector. Then another important consideration. Then two important considerations. Just remarks, but very important, I think. The first is that the terahertz phonons present an energy which is equivalent to the energy of thermal neutron. You see that with 0.025 electron volt, we have 6.0505 terahertz, around 6. But 6.24 is the divine frequency of uranium. So in some way, it's a reason, in some way, this correlation can explain to us why we have so big cross-section of the fission of uranium 235. And then also interesting, calcium and iron. Iron and calcium, this order. Iron is 7.77 and the calcium is 4.79 terahertz. So you may imagine that phonons, statistically speaking, of this with this frequency can interact and in some way, but can interact with the lattice, atomic lattice, of course, not with the nucleus directly, but with the lattice. You can have a real resonance phenomenon, and this resonance phenomenon in some way can take us to this type of nuclear interaction of reaction. So this is the logical chain from instability, nanomechanics instabilities. There are vibrations or phonons, then LAMB, and then lastly neutron emission, which was our first observation 13 years ago. So I want to thank sincerely the project that now is supporting this research since 1 year about, which is the European project called Clean Energy from Hydrogen Metal Systems, which is guided by Professor Chesky, which is here, and I thank personally about this very brilliant guide of this very important project, because it's the first financial aid in Europe. Then there is my book. I give some complimentary copies to some colleagues, but I also one copy if you are interested. The remaining is I can give you this copy of the book that I wrote some years ago with my colleagues. It was very important work of collaboration between 15 people, different areas, different disciplines. Thank you very much for your.
Posso parlare in italiano? Anche in italiano. Allora, se avete fatto prove anche sul pufo con un materiale, e poi se le risonanze del nickel, visto che sono belle, è possibile anche ottenere risultati con subarmoniche più.
Sì, nickel effettivamente, come dicevamo anche, answer in English, yes, is asking me if also nickel is involved in this kind of resonance, etc. Have not the divine frequency of nickel is not difficult to have it. I think in many cases of the order of some terahertz, in any case, but we can compute it very exactly. No problem. Nickel is like iron and calcium, very important. It's the most important ferrous elements after iron. So it should be very opportune to do that activation. Thank you.
My question is make also one comment. My problem is yeah. Okay. My problem is that nickel and iron isotopes the strongest bound nuclei. Okay, the energy per neutron, fighting energy is about 9 energy. So if you want to have a fission of that, you need about 200 megaelectronvolts to fission one neutron, iron or nickel, into aluminum or silicon. So it's a large number, very large number. If you compare it to terahertz frequencies and the energy compared to thermal energy, so you can destroy the lattice, let's say, of the solid of the body. You can lose stones or rocks and stuff. They can move, of course. And degradation, I think, is something what is very, statistic method. I agree that neutron emission or alpha particle emission about fission here. Of course, if you have so many neutrons, you should explain what is the origin of the neutron. But maybe there are some different possibilities for explaining. Okay? The first one, and then there's only one point. The point I would ask you, you have performed some progress experiment, and you have estimated the total energy per bubble. So the question is, it is very important to study theoretically this experiment. What is the temperature that of the chambers that can be reached during the employment? Because it is something that can say us, we can distinguish them between hot fusion and cold fusion. Yeah, this is something what is very important to take place. This is one point. Another point which was very important, and maybe there are some new results, is branching stage of alpha particles emitted and neutrons. So your results show us that alpha channel is a little bit weaker compared to the neutron channel. So this is something what is a little bit different compared to other results of this people. But it's very difficult, of course. So we should think about the experimental results and start to, or try to explain the results. So this, there's also another question. One was the temperature, and then another question will be, because you have determined the counting rate, but what is important to have the branching ratio, total branching ratio. Thank you.
Yes, thank you.
Sorry, but we're running 10 minutes late, so I'm the next speaker.
Yes.
That's fine.
Okay. Yes, if you have questions, I can say that. Okay, I understand you that should have, according to the current theories, we should have a lot of energy locally. If we have fission, we can provide energy. I know that. And one of the explanations could be that, for example, in metals, it's very difficult to have some forms of emissions and energy in the metals because are fertile and they don't break in a localized fraction. But rocks and the materials in general, like hydrogen and brittle palladium and so on, you have very localized failure points, and so maybe that the energy is concentrated in that surfaces or in that points. So maybe a formal explanation. If you want, we want a set explanation based on current concepts. And the concept of resonance, in my opinion, is very important. Today is nearly absent in the fission phenomenon, so resonance is maybe should be important to consider in the future. I think in the theoretical research, not as a done just a remark, but just constructing theoretical models, consider resonance in an exclusive way. So about other points, I understand your doubts, but I think there's some explanation, or we can maybe explanation for any of that. We can speak about.
Can I make a comment or a question? I get answers for it. Very short. As you know, all the isotopes of iron will not react the same way. So do you have any data about the moon, the concentration of iron on the moon or Mars, so that you can compare the Earth with the interaction concentration?
You are asking me about this? Yes, yes. No, in the literature there are data, not my data, but we consider this data very interesting. In Mars there is a very clear transmutation of nickel into iron, very clear, because +1, -1, no? In some way, iron, which is the most important, was a 14 at the beginning, and then last.
I just don't have to say from the very beginning of the Earth to now, some of the editors
There are very important studies of NASA about that. If you wanted to, I can give you the, of course, yes, very important studies about that.
Thanks, Professor Carpinteri. Now is the moment for Police, Bill.
Please your presentation. In the appropriate place. Police la prima exotica. Police discuss global neutron. Neutron? Yes. I don't really want to transmit this. You can move the mouse. Yeah, because well, this talk is about an explanation, hopefully a comprehensive explanation. I think that's a little bit ambitious for the observation we make, which we call cold fusion or condensed matter nuclear science, or low energy nuclear reactions. And I invoke one miracle in this, which is the existence of so-called exotic neutral particles. And we derive their properties from what we observe, which is to say the mass, spin, parity, and no charge. There's no charge, because with a neutral particle, there is no Coulomb barrier, and so there is actually no cold fusion. And there are very high nuclear cross sections for reasons we'll see in a moment. We don't know the exact masses of the neutral particles, but we can calculate the differences because we can measure that from the energy released in a reaction. A typical prototypical reaction is the use of deuterium here, which combines with a neutral particle. This strange notation is actually Yuri Bazhutov's notation for his erzions. And as I rely heavily on both his theory and on the theory of John Fisher, his polyneutron theory, both of which shuttle neutrons about, and they can react very, very quickly with appropriate donors and acceptors because they're neutral. So I assign appropriate spin parity and masses just according to this first equation. We know the spin and parity of the deuteron and the proton, and the difference is going to be the spin and parity difference for the two neutral particle species I've got here. So in this particular case, deuterium behaves as a neutron donor. It becomes a proton and has added a neutron to this species here. And of course, there is no radioactivity. But if this reaction occurs, we're going to consume this species and we're going to create this. So to complete the cycle, we have to reverse it. In other words, we need to regenerate the catalytic neutral particles. And this is how we do it. Common acceptors of neutrons, nitrogen-14, carbon-13, silicon, sulfur. These are all rather common isotopes in experimental setups. But there are other ways too, and we'll see in a moment. So in order to get a chain reaction, we need neutron donors, like deuterium, neutron acceptors, as I've just shown, and some source of exotic neutral particles. And I'm going to leave the discussion of where we get those exotic neutral particles from in due course, maybe at the question time, because I'm sure I can see Adrinia here looking at me, and I think we could talk about it for a very long time. One interesting aspect is donors and acceptors usually have an odd neutron number. That's because the extra neutron, the odd neutron, is not quite so strongly bound as an even neutron would be. And that implies that the proton number, the atomic number, must be even. And that's because there are only 4 stable odd nuclei in nature. And so as a rule of thumb, you could say these fuels, these donors and acceptors, are going to have an even number of protons and an odd number of neutrons. There are some exceptions to that, which we'll see, and they're very interesting exceptions. So again, the prototypical reaction is the shuttling of neutrons. You have X, which has an atomic number, mass number of A, and it changes to plus or minus 1. In other words, we transfer 1 neutron at a time. Because there are 2 products, we can simultaneously conserve energy and linear momentum, so it's much less likely that any product is left in an excited state. Okay, I think I've covered that. One reason why we don't get too much radioactivity is that the product, after adding or subtracting a neutron, becomes an even nucleus, and these nuclei are particularly stable. Furthermore, the amount of energy involved in these transfer reactions is very modest. Often it's less than a million electron volts. And so there's less energy available to move what is already a stable fuel isotope into an unstable product isotope. So it's not entirely a coincidence that we don't get radioactivity. But again, we'll see the exceptions. So let's look at the palladium system. And it would appear, even without any deuterium at all, palladium could produce some energy, and we could complete the cycle. So for example, we consume this species, and we produce this one, and then we can recycle it again with another palladium isotope. And as I said before, it's an odd isotope, palladium-105, which has an odd number of neutrons. And these isotopes have already been observed to be depleted. I've mentioned Zhang and Dash here, but I think Mizuno also has reported that it's depletion of palladium-105. What about helium-4? That's meant to be a well-known product. Some rather unusual reactions here, which produce more than 2 products. For example, the first one with lithium-6 effectively produces lithium-5, which immediately emits a proton, but we get helium-4. I've included lithium-7 for completeness, which just regenerates more lithium-6. So we would expect overall a depletion of lithium-7, and we can't be sure whether lithium-6 will increase or decrease. Beryllium is quite a nice one because it has a very low binding for the extra neutron, but alas, it doesn't conserve spin parity. On the other hand, boron-10, and boron is ubiquitous in glass, and therefore present in a lot of systems. It's also used as a dopant in some palladium electrodes, produces 2 helium nuclei and a proton. So actually, the first and the last reactions are producing helium and protons simultaneously. It'd be really nice if we could demonstrate such production. But the first question is, hey, if we need lithium, where does it come from? I don't know if you recognize this nickel rod. This is from Piantelli's laboratory. And you can see here, as a rather strange white band, which is almost certainly lithium carbonate, but I think he used lithium hydride back in the 90s, and this is merely weathered over the decades since then. He never reported the use of lithium except in a patent. So he wasn't entirely open about what he was doing, and I think this may be the case for other gas loading experiments. People have used a recipe which they haven't been public about. The classical heat over helium ratio is supposed to be 23.847 million electron volts, which is the expected energy of the fusion of 2 deuterons. But if we examine the table of isotopes, we can see we can make 23, 24, 25 within the error band of energy per helium in countless different ways. And this reaction here would only be valid if it was the only reaction taking place. Almost every model of cold fusion predicts multiple reactions. We also know that prodigious quantities of energy are produced in systems which in theory have no deuterium at all, only the naturally occurring deuterium. And so we don't expect that this particular ratio has any significance at all in cold fusion. You cannot use the heat over helium ratio to make any conclusions. This is also from Piantelli's laboratory. This is a cloud chamber experiment. This is his nickel rod, and you can see one particle coming off here. It's obviously a heavy particle because it interacts with a gas nucleus and gets deflected. And this track is about 8 centimeters long and believed to be a proton. However, when Piantelli did this experiment, at first, the number of particles coming off from his nickel rod were like a Christmas tree with pine needles going everywhere. There were so many tracks that he couldn't possibly photograph them. There was just a mess. You couldn't measure the length, because when you look, you could only see the longest tracks. After a week or so, the tracks were about one or two a second, and after 2 weeks, they were hardly visible. And so, in other words, we have some reaction which was continuing long after the hydrogen was removed and gradually decaying. And the fact that the protons and also some alphas were coming off simultaneously. I can't show you a picture of the alphas, but the alphas had a much shorter length. So they were very short, lower energy alphas, and there's no alpha decay, which produce low energy alphas. So there must be another explanation to the source of fast alphas. And I can tell you what that is. Well, I told you what it is actually. Because, well, let's go back just a moment. It's this reaction or this reaction. In this first one, the protons will take off most of the energy because they've got full net available. But in this last one, there's a very, very low energy. So we can make protons and alphas very, very low energy. And in the case of, do speak up.
What's the energy of the proton on the floor?
It's going to be less than 100 keV, isn't it?
It's a continuous spectrum. There's no isolated time for that, because if you have 3 particles in the final channel, you have no isolated state.
Yes, exactly. Yes, yeah. Absolutely right. It's a pity we don't have sufficient photographs to be able to see what that spectrum would be, but that's a very good point. So I've covered palladium. Let's look at nickel. The first reaction actually produces some radioactivity initially. Nickel-59 has a half-life of 76,000 years, and a tiny proportion of its decays produce positrons. And so there would be a very low level of 511 Kev annihilation gammas. And again, Cantelli, who was working extensively with nickel, found that the 511 Kev energy in the gamma spectrum, but it's only about twice background. I think we need to do the calculation to see whether this is a reasonable number or not. But I think something twice background can so easily be an error. I wouldn't be too enthusiastic about that. However, for the other two reactions, there's no radioactivity at all. I showed you this picture 2 days ago. This is again the nickel surface, which rose in temperature to over 1,000 degrees. And I think this is important because it means that whatever was causing the nuclear reactions which melted the nickel, they were occurring in molten metal. And molten metal means there's no active site, and it means that the exotic neutral particles were perfectly immune to high temperature. And there's another, even more fundamental conclusion. To get a hotspot, that means there was one particle doing it, which is why you get individual hotspots, because there's only one particle there doing it, and it has a very, very high cross-section for the reasons I've just said, and so it all makes sense. It might have a mean-free path of a few microns, and after a while, it does so much damage locally that it melts. It's Jacques Rouet did the calculation, I think in Toulouse, right? And you showed that 10,000, perhaps on a big hotspot like that, 100,000 reactions might be required. And here we have good evidence of a single particle performing absolute miracles. So what about, if these particles exist, why can't we detect them? And the answer is, we have detected them. It's just what we call the neutrons by mistake. Because our typical neutron detectors, like helium-3, boron, or gold activation, are all activated by exotic neutral particles. And I've supplied the appropriate reactions here. So they react with helium-3 to produce a couple of protons, or with the other, the neutron carrier, to produce helium-4 with quite a massive 12 MeV of energy. And we can expect these reactions, just like with ordinary neutrons, to have a very high cross-section because there are two products. So neutron detectors, even helium-3 detectors, are going to detect them with a very high efficiency. Same goes for boron. And in the case of gold, which I thought I'd add for completion, it's a different isotope of gold which gets activated here. It's not the gold 198, which would be the case for a neutron. But if that all you're detecting is some gamma counts from activated gold, it's very, very easy to make a mistake. So I'm suggesting that the neutrons we typically detect in our systems are not neutrons at all. They're exotic neutral particles, which in some way have been released. And again, I think at question time we'll be discussing how they get released. Just for comparison, this is how conventional detection of real neutrons works. So helium-3, boron, and gold. There's one difference though. Sometimes manganese-55, which is natural manganese, is used to detect neutrons. They will not detect exotic neutral particles. And so you can distinguish the two. What about tritium? Well, I've already mentioned how ENPs can be misidentified as neutrons. It's also possible, given that tritium is conventionally measured but in a scintillation counter, just by counting flashes of light, that it could be some other beta decaying isotope. We shouldn't jump to conclusions. Just because you have an instrument which says this detects neutrons or this detects tritons, tritium, we should have an open mind and think we just might be mistaken. It's quite difficult to explain how you get tritium, Because if tritium came off at any high speed with energy, it would react with any other deuterons in the system. And of course, we're measuring tritium in a deuterated system, and we don't see the 14.1 MeV neutrons, which we would expect. So this is rather good evidence. We've misidentified the tritons. Well, I was mentioning 2 days ago the kind of acid test, whereas you see what, you try and analyze what happens when these exotic particles interact with naturally occurring isotopes. This is an absolutely fundamental test for any theory, and I mentioned how you could apply it to the Witten-Larsen theory, to the hydrogen theory, to the Imamura's theory, to Jean-Luc's deep direct levels, and so on. Anyway, the Erzion here, I call it an Erzion, exotic neutral particle here, reacts with 11 stable isotopes out of 286, not a great deal. And the other species reacts with 13. Bashutov will call this anion, but I don't like to call it the same particle because these particles of mine have rather different masses and different properties. And of these 11 plus 13 is 24. Of the 24 products, only 3 are radioactive. 3 out of 286. This explains why we don't see radioactivity. It's predicted. I haven't invented any parameters to get to this conclusion. This is what we expect, and this is what we observe. And if we apply this test to any other theory, we get masses of radioactivity everywhere. So we know these other theories are not correct, or they need refinement, shall we say. I should say, I've assumed that these reactions are conserving spin and parity, because if they don't, they're going to be dramatically suppressed in rate. So I want to look at the most probable reactions. So, what have we actually measured in terms of radioactivity? And I think this was at ICCF4 in Hawaii. Bush and Eagleton reported electrolytically induced transmutation of blah, 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 of rubidium carbonate electrolysis with nickel electrodes. And when I look at the 3 radioactive products, rubidium-86 is one of them. And it has a half-life of about, I think it's on the next page. No, it's not. 15 or 16 days. And that compares with the appalling calculation of half-life with inadequate apparatus instrumentation by Bush and Eagleton. They calculated 3.5 days. But if you look at their curve, they have millions of disintegration counts. It goes all over the place, which is impossible. You know, that we would expect the square root of a million, let's say 1,000 to be the typical variation, and it was changed by hundreds of thousands in the space of hours, both going up and going down. Probably with some segregation in the cell, and we can't really tell what the real half-life was. So this is an experiment which needs to be verified with proper instrumentation. They did use a sodium iodide multi-channel gamma spectrometer, but it only had 32 channels. So again, they couldn't detect the energy correctly, and they then made no estimate. Another prediction is radioactive chlorine-36, which has a half-life of 300,000 years, and in 0.03% of those rather rare decays, you get positrons, which can be easily measured, perhaps they have been measured. Chlorine is probably a very common contaminant in our systems. In Stromanis' lab, we detected hydrogen chloride just as the hydrogen in the nickel systems, just reducing the chlorine on the surface of the nickel, and it's easy enough to detect. Ed Storm says that chlorine is not a good thing to add to electrolytic cells, so most people don't. But Mel Miles did, and he got counts on his Geiger counter. Why he didn't examine in more detail the energy of these counts, I don't know. But I think he was probably afraid that the nuclear safety officer would shut down the lab. But if you get any kind of radioactivity, you ought to analyze what it is, or not just for your safety, but because of the scientific possibilities of discovering something. I'm very grateful to Alan Smith, because he pointed out to me that another prediction, that is to say, the activation of molybdenum 100, has also been published. So we now have 3 radioactive predictions, and they've all been verified in perhaps not with the greatest detail, not with the greatest precision, but they, qualitatively at least they've been verified. So we have molybdenum, which is acting rather strangely as a donor of a neutron, but it's a very heavy, stable isotope of molybdenum, and it produces radioactive molybdenum-99, which then decays to technetium-99, which then decays to ruthenium. But this second reaction here, molybdenum, has a very nice half-life of 66 hours, so it should produce a very high count rate, and the energy of the gammas is 739 keV, so very easy, very penetrating gammas that easy to get through any apparatus, whereas the technetium-99 has a very long half-life and a very low energy. I don't think we're going to detect that. It'll be absolutely dwarfed by this first signal. And again, this has been half verified. So this is another experiment which ought to be done yet again. In fact, all 3 experiments should be done yet again. So let's recapitulate a little bit. We need a heterogeneous system which consists of donor isotopes, acceptor isotopes, and some source of exotic neutral particles. Again, at this conference, it's been very helpful to talk to you experts like Jacques Rouet and Bob Grenier, because when you impregnate a metal with hydrogen, you change its magnetic properties dramatically. And there's a particular case in the literature, which I was quoting yesterday, of loading up Sumerian cobalt-5, which is a very strong ferromagnetic material. It's used to make those supermagnets, and it absorbs hydrogen very easily. And by subtly changing the external magnetic field, you can drive the hydrogen out, because the pure metal wants to take the magnetic field, because it goes into a lower energy state. And just by changing the magnetic field, you can drive hydrogen in and out. So we know hydrogen has a dramatic effect on the paramagnetic or ferromagnetic properties of these metals. So this leads one to make a conjecture, and it's purely a conjecture, that maybe some exotic particle has magnetic properties, and we can manipulate them by applying magnetic fields or even radio frequency magnetic fields. And if we move them around, which we can also do with fractures, with applying pulse electrolysis, changing temperature, changing pressure, we change the properties of the metal, maybe around the mercury temperature perhaps, or maybe not. But in addition, with the addition of hydrogen, we've got all sorts of combinations to make things rather complicated for ourselves. We could be moving the exotic particles around. And this suggests that if we want a source of exotic particles, all we need to do is take a supermagnet, dissolve it in acid or something, and the magnetic properties will be destroyed, and it will release into the environment, close to your experiment, all the exotic neutral particles you could possibly want. So, in conclusion, we can explain helium and isotopic anomalies over a vast range of heavy isotopes. We can explain palladium and nickel, titanium, tungsten, platinum. We can we predict and we find penetrating gammas, and we need to understand a bit more deeply to what extent spin and parity conservation are actually required in the condensed matter environment, because maybe the rules of high energy and vacuum physics may be slightly different. But I think that the ENP theory explains a lot of our observations. So, are there any questions?
Yes, sir. Do you have a receipt to make an EMP generator?
No. But I told you just now, if you dissolve your magnet, you'll find the magnet has already absorbed them.
I can answer that point. Fine. You want to do it now? You saw it yesterday. If you look at the paper by Bogdanovich from 2019, he says that the magnetic monopoles are taken off of the surface of the magnet to get rid of the electrons by the gamma rays. I've been interested in this field since 2008, and I heard a lot of crazy things over the years. And I must say that it's the first conference that I start to get a sense of how many weird observations we have been seeing and have been reported all over the years. Because I've been to many ICCs, many conferences, many field conferences, organized conferences, and yeah, it's really the first time I observed that there's enough evidence and enough observations, and we start to have a robotic integration of these exotic particles. And well, I think it's interesting, and as we move forward into the prediction of those and the characterization of those particles, and we will be able to actually have a better understanding of the physics of that. So I'm glad it's going on. My question is how you would like to imagine what is the composition of this new neutron particle you want to have? This first question. Another question, if you study some transfer reactions, neutron transfer, you should look at or test of that. You should the proton transfer reaction should have very similar probability.
No.
Why not?
Because if you've got an extra proton, you've got a Coulomb barrier. You'd have a Coulomb barrier if you were transferring protons. So you
No,
can't.
you have no Coulomb barrier because your neutron particle can transfer
Well, how
proton
can-
or neutron by the same.
Okay, what neutral particle was transferring proton?
Yeah.
Which one?
From the target. You can transfer proton from the target neutron to the neutral particle, and then this is just the problem. You have
Then you've got a Coulomb barrier for the separation of those particles.
that so the problem I have is if you assume that you can transfer neutron from the target to this neutral particle, the same probability of similar probability you should have a so-called proton transfer.
I repeat, you've got a Coulomb barrier for the separation of the particles.
And then, no, that's from physics. If you study, let's say, neutron-specific reactions, you have very similar probability for transfer of neutron and proton. So you have a pickup reaction and difference of this kind. So if you follow this idea that the proton and neutron transfer have very similar probability, then finally you have no neutral particles anymore. All the particles.
Yes, that would be correct. Yes.
Okay, so this is the first point. Another point is if you, what is very important is you should think about the mass of the neutral particles, because if you want to predict any energy or energy production, you should include, of course, the mass of the particle
As I explained, it's the delta mass which you can calculate. You can't actually, not the absolute mass, because when you consume one exotic neutral particle, you create another. So all you're interested in is the difference in these masses.
Yeah, there's the Q value, but this Q value will be distributed between all the particles. If you have only two particles in the exit channel, the whole level will be distributed.
Yes, of course.
And therefore, it's very important to get a mass of that. You can predict, for instance, some reactions and say, from this reaction, we can determine the mass of the neutral particle.
No, all you can determine is the changing mass of the neutral particle. You can't determine the absolute mass.
Okay, so there's another point. And the third point I would have, maybe suggestion, okay? Because if you present only possibilities of some reactions, it's not enough. It is much more important to have some numbers, because the different reactions will have different probabilities. So even some of them can occur, it doesn't mean that they are probably enough to measure.
Okay. I've written some software which examines every possible interaction of these neutral particles with every possible stable, naturally occurring isotope on this planet. That's how it makes predictions. So it's an exhaustive study.
Just one very short thing. Can we call them arsons in memory of because the Russian society is the society on coal, nuclear energy, and volcanoes. So it looks to me like they got it from the. It's just a proposal.
Well, I covered the epsilon theory 2 days ago, and there are some criticisms I would make of Bajutov's. Yes, and I certainly recognize that I've inherited the ideas of Bajutov and Fischer in getting this far. The very big difference here is that my exotic particles bind the neutron much more strongly. And this is the way you cut down on the radioactivity. Because the amount of energy available for a reaction is very limited.
Now, if you answer your point come out in terms of prediction of number of reactions, you have to look at the past data because if you study energy, one spot, what I did, you have a number of reactions needed to get this energy. But it's not enough. Because what they said is, okay, you can say that some reactions are necessary to make, but the problem is you should have numbers, so cross-section, and compare this cross-section with other cross-sections of other numbers. And then you can conclude something. Without numbers, you cannot conclude anything, okay? This is only my point. This is also your point, because you want to compare theory with the experiment. And it's necessary to have the numbers, not only the concept or idea. Finally, what we need is our number, and then the numbers can compare. So if we speak, for instance, about neutrons emission, alpha particle emission, we should have a branching ratio. So what is the branching ratio between alpha and neutron? That we can conclude, or we can compare with every kind of theory. Without this number, you cannot do anything.
We need to do the experiments, I agree. But you start off with a theory, which makes predictions, and then you try and verify those predictions.
We need some experiments that deliver some numbers. And then the numbers...
Yeah, I agree. We've always agreed about this.
You mentioned Bill, the possibility of dissolving Sumerian Mountain magnets in strong acid. As I've done some experimental work with this material, I can tell you that it's not necessary. If you electrolyze unflated Sumerian Mountain magnets in, for example, lithium heavy water, they will turn to sludge. You end up with a cathode that hangs together because of its magnetic field. But nevertheless, it's completely devoid of visible structure. I understand the under a microscope, but it's kind of amorphous mass of hydride Sumerian cobalt. Then, if you were to put it into a container for some time, and you heat it up to around about 800 degrees, which seems to be necessary for some reason. And then as it goes through the 300 degree temperature zone, you'll get a burst of very weak gamma, around about 78 current in Iran, it's a repeatable phenomenon, just within a particular design. Puzzle there out later, but perhaps got some relevance to your theory.
I think that might be the Sumerian then.
Very likely. It's fairly high in Sumerian and alloy actually. Yeah, very close. But it does work. No strong answer to find. It's a very simple experiment.
No, I just mentioned that as a simple way, an intuitive way of doing it. It's probably not the best way. The next speaker is Bob Greenyer. I'm sorry, Bob, we're half an hour late. I think I will postpone the following talk till after the coffee break. No, yes, there will be a coffee break, yes. At 11 o'clock. Sorry.
I'm going to put that video down. She needs to stop the streaming. I want to thank everyone for still being here. I hope you will be if I get to the end of what I have to say today. I feel deeply, deeply honored to be able to share this with you. I don't know why it was my opportunity to do this, but anyway. I'm sorry it's going to take a lot of adjustment for people. Sorry. And I'm also concerned about what it implies. Okay. I just want to check on recording. Okay, thank you. My name is Bob Greenyer. I'm a volunteer with the Martin Fleischmann Memorial Project, and I am here to talk to you today with a microphone, hopefully, if I can get one. Okay. So I'm here to talk to you about coherent matter traveling wave beams and their possible role in making strange radiation tracks. If you don't know what strange radiation tracks are, I'm going to give you a couple of links. You can go and research this afterwards. But basically, they were first observed before 1992, but put into the Solon pattern. I'll just show you what was in that pattern. But essentially, it's been 29 years without an answer. Okay, and hopefully at the end of this presentation, there will be an answer. Okay, just to follow on from the last presentation, I spoke about SDL in my previous presentation at this conference, and this is a very important finding that we have. Don't bother reading it, you can see it in the slides later. But essentially, what you're seeing down there on the bottom right is a little glowing spot and then a not so glowing spot after 4 seconds, with an atomic mass of 400. With an atomic mass of 433. Okay, I get it, slow. Slow?
Can you speak Italian English?
So he reported this, I believe, in 2006, and it was one of his accretion disks. Now it is a 1/10 of C discharge of about 300 joules into a target. It is a discharge. Therefore, it is an exotic vacuum object. An exotic vacuum object is ball lightning. And on the accretion list, a long time afterwards, they put it into a secondary iron mass spectrometer. And they fired a beam at the thing to determine what the elements were. Well, they found a number of spots where they couldn't determine what the element was. And so they've got a limit on their spectrometer, so they know it can't be lighter than 433. I think that's how it works. Anyway, so But then they thought there was something wrong with the equipment because they couldn't even observe the primary ion. And so they turned it off, and what they observed is what you see down in the bottom right, this glow that then decayed where they were targeting the beam. So they turned it on again, and they fired the beam, they turned it off, and on the photon multiplier, they saw this exponential decay again and again and again. They don't know what it was, but the ions that they were firing into it were disappearing and emitting light in an exponential decay. A long time after they did their experiment. Okay, so my plan today is to discuss the methods of coherent matter production, briefly, behavior of balls of fire and on and in metals, behavior of observed traces versus witness marks, the product from a dead coherent matter traveling wave beam. I only observed this on Tuesday, so it's very preliminary. And I've got a special food at the end. What you're seeing on the right is something you can hold in mind. It's the NATO model from Matsumoto at the bottom, which he came up with, but later he concluded that it was ball lightning, a type of ball lightning, and you can see the ones that we observed on the Amasa vibrator plates. So the overall overview of the process is it causes electron bunching. Whatever you need to do to create this, you have to create electron bunching. That leads to coherence and monopole production. Then you get self-organization of that coherent monopoles and the coherent matter, and then you have to pump it with energy. If you pump it enough, you'll get more interesting nuclear reactions via the self-collapse. And then you get production of strange radiation post-collapse and disruption. It kicks out these particles. And then observation of witness marks and dead material is how traditionally people have observed this. They've only ever been able to see what it did to a piece of material somewhere else in their lab or in their apparatus or in their head. Right, so Lockheed Martin published a patent called Systems and Methods for Generating Coherent Matter Wave Beams, and you can see the conclusion of what it can do. Examples of applications are a more accurate global positioning system, matter wave projectiles and missiles, directed energy weapons, matter wave optics and cloaking. I'll leave it at that. You can read it in your own time, but it's freaking scary, to be honest. And when you see what the bullet is, it's going to scare you too. So they say in the patent, it's very clear, and it was a watershed from my understanding as well. Normally, Bose-Einstein condensates are formed by cooling, say 133 cesium or 23 sodium atoms to near absolute zero. The purpose of this is to get the same de Broglie wavelength for those single isotopes so that then they will cohere and create a quantum macro object. The Lockheed Martin patent argues that all you need is the same matter type, the isotope, for instance, 27 aluminium, and even an electron. It's going to freak people. At the exact same temperature, the same de Broglie wavelength of the overall mass, in the same phase, and this leads to a matter wave coherence, which can be assisted by employing the 1950s proposited Aronoff bomb effect. Leonard can work from absolute zero, which is pretty much what it was doing when Piantelli observed his reaction in 1989 at Palo di Siena on the 18th of August, I think it was, 1989. Because he had a nearly liquid helium cooling his biological experiment. To dense plasmas at any temperature. So this is not a process necessarily that needs the system to be hot. It just needs to be all of the material that can cohere is at exactly the same temperature. So you need to remove degrees of freedom. Okay, so the US Air Force on ball lightning in December 1993 fusing technology. In one part of that thing, which you can go read in your own time, they say the fact that nature produces ball lightning without costly or complicated equipment is an encouraging indication that once we understand how ball lightning is formed, the equipment needed to produce a ball lightning fusion plasma will itself be simple and require only relatively simple containment equipment by current standards of magnetic fusion research.
That's good.
You're a funny boy. So the US Air Force on ball lightning, they did a study that was commissioned in October 2001 to find out anyone in the world that knew anything about ball lightning and related technologies. And the conclusion was the classified 1950s to 1960s Air Force funded research, which remained classified in that report, and the work of Ken Shoulders are the most promising areas for further study. Shoulders began examining the plasma vortex at force-free plasmoids, work of Wells and Bostic from 1956. He was trying to get the H-bomb to be domestic fusion. Because he was originally influenced by the theories of elemental particle structures formed from vortical flows of a primeval substance. I'll skip to the bit. Can possibly generate, the fact that an EV, that EVs are a form of microball lightning that can bore through and even destroy by explosive impact solid materials, can possibly generate more energy than is required to form them, are point sources of copious X-rays, and are compact, self-contained balls of condensed, high-density charge, demonstrates a clear need for further research to investigate their potential applications for weapons, defense technology, and aerospace propulsion. And the lead author there is Eric Davis, who is a colleague of Hal Prithoff on the Sapphire project, which is what this talk is about, a kind of replication of that, but we did fast, dirty experiments and learned a lot cheaply. So Shoulders, so how do you make an exotic vacuum object, and what is it? Any spark has an exotic vacuum object out in front of it, and you saw that in George Eagley's presentation going back to, I think, the last 2 centuries ago, the end of the 1800s. An EVO can be conceived of as an atom without a nucleus, or as a spherical monopole oscillator. EVOs exhibit a survitron behavior with a number of densities equaling the Avogadro's number. These non-neutral electron plasmoids can contain various levels of binding energy, which exceeds that of atoms and allows the new types of reactions with matter. This monopole oscillator is the perfect generator for vector and scalar potential waves without contamination from either E or B fields, and you will see that behavior in the videos I will present you. These waves can be thought of as longitudinal waves in the vacuum. They are largely undetectable by the standard EMV detecting means, but are readily accessible in the monopole world. So it would not be fair, and George mentioned him, to not mention George Messias at this point. He was ahead of the game long before Hutchison did his work that spurred Ken Shoulders to do his investigation of what happened with Hutchison. But he first reported in a US conference, I think in 1996. I've got the 1997 and the 2004 version of the paper linked in the presentation. But in the 1996 paper, you can see explicit descriptions of how to make electrons, which are explosive electron emissions. Okay, and I think you'll recognize every single way to do LENR, and it was in the paper in 1996. So you've got microperfusions. That is how the Parkmore 225-day reactor works. You create these exotic vacuum objects. They can go and live in the liquid metal, and they can do the transportation, even though it's a liquid. Dielectric inclusions. This is what you do on your wires, Talani. You add sol gel. Oxides and other inorganic electric films, and that's what you will be doing at Conrad, I should imagine. We're talking about that to enhance your screening energies. Absorb gas layers, grain boundaries. We're going to see this in the exact process going on using the grain boundary example. Microparticles, oil vapor cracking problems. There's been problems in the fracking industry. Not fracking industry, the fractioning of oil, and it is probably due to this. Edges of craters formed upon breakdowns, which is what you do when you pre-treat electrodes, and causal cracks. Well, we've definitely heard that before. So I'm going to talk briefly a little bit more about the Solin patents. There's an commercial electron beam furnace, the sort that David Hudson used to make a thumb-sized tungsten electrode disappear instantly twice, with radiation that turned his glassware into dust in the far reaches of his lab. Spontaneously proceeding low-temperature nuclear process with the excitation of self-sustaining controlled chain reactions of nuclear fusion. Functioning under conditions of combined electromagnetic, gravitational, and nuclear interactions in a mass of nuclear fuel generating directly in nuclear fuel coherent radiation and superconducting currents of magnetically charged particles, obtaining superconducting nuclear material and nuclear fusion product with the chemical elements formed in the process. And I list all of the paramagnetic, low vapor pressure, high melting point, suitable materials that he used in his now free to use but awarded patent. So the Sodium patents go on. This process is accompanied by the occurrence of self-sustaining chain reactions, with the participation in this process of composite particles of nuclei, protons and neutrons, external electrons, atoms and other elementary particles inside the nuclei. Ultimately, as established by the author, a spontaneous process proceeds in the volume of the liquid bath of metal, leading to the transition to a new aggregate state with the formation of superconducting superfluid nuclear substance and the nucleation of magnetically charged particles in it. The physical result of the process becomes the recording device and the detector. We have replicated every single observation of Solin in something that wasn't a big arc furnace. It was a very cheap device a number of years ago, before I ever knew about Solin. Magnetic charges that automatically arise are maintained in its volume, and they lead to the decay of protons and are catalysts for nuclear reactions. This has been observed by IWAHLM, and it's been observed, I think, by one other party. So you've got meson-stimulated transmutation and muon catalysis, and you've got a whole smorgasbord of things you can do. With increasing concentration of magnetic charges in the active medium, the intensity of the course of the nuclear reactions increases spasmodically. This is achieved by creating conditions for self-compression, the exact same words of Sviatodenko and of Matsumoto, of the mass of superconducting nuclear condensate. And on the right, you've got the zirconium fuel, which is his preferred fuel, and the zirconium fuel afterwards. If you fire an electron at zirconium in a hydride or deuterated environment, you're going to be doing this whether you like it or not, or have an opinion whether it's happening or not. Solin patents. Due to the formation of the mobile active centers domains in the active medium, they have the form of hollow spheres and cylinders. Inside them, nuclear fusion reaction occurs. Now, that is from his 2001 patent. This is Matsumoto with the hollow spheres, with a nuclear reaction occurring inside and converting the material into carbon, which sprays out. This is on our Vega experiment in electro system. And then I talked about this, the titanium in the explosive coherent production of crystals with voids, and these structures that are coming out, which have a cone and a rod. Magnetically charged particles are generated and accumulate with the generation of superconducting currents. Electromagnetic, nuclear, and gravitational forces are combined with the formation of coherent radiation, which was what burnt Piantelli in the 1990s on his arm when he started a reactor. Active sensors whose shells are composed of superconducting nuclear condensate rotate. You'll see the rotation, and the shell, in my view, is the inside of the double layer. Thus, active sensors act as gravity-magnetic rotors in local zones. In the areas of their accumulation in the active medium, superconducting current, eddy currents, and remember I talked about that yesterday, I will show you multiple examples. I said it was important, I said 22, but I didn't read this paper before then. And circular waves with white glow like the Indian, pulsations and local explosions. Orderly directed, self-accelerating mass flows in the form of a cone and a cylinder arise. You have a cone and a cylinder. This is just a cone and this is a cylinder. This is his SEM. It's obviously he had poorer equipment back in prior to 2001, but he has the cone here and the cylinder in the center. So it's just different orientation of the same thing. And that is why they order their arrangement, as I said yesterday. So this is the pretzel, or the magnetohydrodynamic structure that I found in the 7-month running nickel hydrogen reactor that produced, I think, 4.2 million electron volts, mega electron volts and 2.1 electron volts. God, I'm going to get this wrong. A lot of energy. You can go look at that from my IWAHLM14 presentation. You can see it on this Matsumoto structure that was in the previous slide, and you can see this sketched onto the Solin 1992 patent. Active sensors interacting with each other move and join and then increase in size. This process has a self-regulating and resonant character. Under such conditions, nuclear transformations spontaneously activate. propagating from the central zones of the liquid bath to its peripheral. I'm not going to read the middle paragraph. Protrusions and depressions periodically occurring on its surface respond to the maxima and minima of the intensity and spontaneously generated alternating magnetic field, and characterize the appearance of magnetic solitons of two different polarities in the resulting magnetic superconducting liquid. I have for now 3 years observed this on multiple systems, in like from non-contact to deuterium and just a heat one to cavitation, all kinds of things. I didn't know what it was. I put the data out there and then I translated this on August last year. So this is his image with all of the things you can expect to see recorded in your post-nuclear condensate fuel. So the line reactor here, it used, because we saw diamonds in the beginning of 2013 on your wire, Charlie, I suggested the use of industrial diamonds because in nickel or whatever, they come in nickel tinted. And industrial diamonds are better for electron emission because they've got nitrogen pollution, and that improves their emission of electrons. So this is the reactor. It was built by Looking for Heat, which was a venture of our good friend Alan Smith. And it's you have a control and this, and it's just, you have some you have copper wire just as a thermal bridge, but it's very important for the process, I believe. Fused quartz tube, this is Cantal or some other heater resistance wire, Cantal. So here you can see, this is on a classic, so these are shoulders, exotic vacuum object beam chains, and this is a beam chain on the outside of that quartz liner, quite a long way from the core. Here is this triangle. This will become important, but this is one monopole that's starting to eat into the quartz. This is coming from the inside to the outside, and this is on the copper oxide. And in the flux loop of the monopole, you have either synthesized or transported material. In this case, I believe the calcium is synthesized. This is just copper oxide, and you've got calcium in. This was an experiment I did 2 weeks ago using HHO in Switzerland. And the idea is to use calcium because many systems like to fuse to and fission to calcium. It's doubly magic. It seems to be something pretty solid. So I wanted to use that as a substrate and see what would happen when we heated it with HHO. Because of limelight, it's something that's known. And because when you want to dry off the carbon dioxide, you know you've gone past. Not that bad. When you drive past, you have to go past 825 to 850 degrees C to get carbon dioxide off, and then it goes to calcium oxide. And then the limelight temperature is about 2000 to 2200 degrees. And we got the limelight, so we know that we are seeing temperatures, or should be temperatures of 2200 degrees. And according to Parkmore, that will synthesize lots of cold neutrinos. What you're seeing in Solin's pattern is the effect after a coherent center has blown up, and this is what you see. And the interesting thing is, I didn't expect this. I did expect silicon to be there because we observed a huge silicon line when we started burning it, and I thought that was going to be coming from another reaction. Let's put it this way. But we actually found that it produced calcium peroxide and silicon when it was exposed to the HHO, and we got this wave-like structure. Are you serious? Okay. I'm going to start this. I'm not even anywhere close to the punchline. So these are the flux mirrors on the line reactor. These are the polar flux loops, and this is material that was ejected from one pole to another, and it's in this loop in the system. And it has synthesized material. We've seen the monopole here before I showed you yesterday, and you've got the structure there. These are the monopoles that are on the inside of the quartz, and you can see that they have two poles. And when you've got one pole, it rounds material into the surface, and you get a spot. And when you've got the other pole, it pulls material away, but it leaves this very center unaffected. And when you've got the same pole together, you get material flow around the outside of the particular monopoles. And here we can see on the outside of the line reactor, well away from the core, a magnetohydrodynamic structure. And you can see this is on the inside, burning from the inside out. They are exactly the same as he observed. And on the wire that is here, there is a deposit like this, and we will see this if we ever get a chance to present it in the another reactor. But this material is a vortical structure, and it has these crystals which contain calcium, which shouldn't be there. This is what you see. This is a 1950s demonstration of a soliton in water using a kind of mocked-up wing, and you can see it matching the structure of the two structures that I've just referred to. And this is the soliton that I was talking about yesterday in a magnetohydrodynamic structure. And you can see the outside of the ball lightning that formed and this laser cut. You can see it's literally like it's cut by a laser. And that got me onto the idea of maybe it's amazing. And so here is a monopole. That's what it would look like when it goes into a surface, because the core can only go 50% in. And this is on that same 10-yen coin. So you've got this is on this axis, and at 90 degrees orthogonal, you've got a much bigger fractal structure of the ball lightning. Anyway, this is coming in, and if you see here, the monopole comes in, and it's eaten the copper, and it's left the copper just on the rim that protrudes through. So this is an Assisi pattern again from 1992, and I will be able to show you live videos of these effects occurring. And this is the first recording of strange radiation. He says when the area that's doing self-collapse collapses, it shoots out these shock waves on the surface. But I think it's actually not just a shock wave; it is actually these particles, because we can see this exact behavior, and in fact, all of the behaviors of all strange radiation I will be able to show you today at some point. What's he saying? Yeah. This is the ball lightning trace on a Hutchison sample. I was meant to show the magnetic monopole theory that was suggested in the 1980s for how Hutchison achieved this effect by the military and how it occurs, but that will have to go to the slide that I published. So this is just a bit of fun, and maybe I'll break at this point, but this is a Sumerian Mountain, which is possibly as much as 12,000 years old. And it was in an Iraqi museum. It has the Sumerian ordered structure on the top. It has the symbol of well-being and auspicious nature, in which I lived with all over India. And the wonderful thing about it is, because it's going around here, it's a coherence down to the point. It has the ring which you observe. It has the two particles out of coherence in relief, embossed rather. It goes round the loop, round the coherent direction, and it comes out in relief. So whoever made this mass-produced thing that produces light, a lantern, knew precisely how this technology worked. And here it is on a 1986 sample we called the ball burn since we've had it. And you hear see the magnetohydrodynamic structure, I call it yin and yang. And there is a mirror of this on every Indian temple. And you see the structure in this structure here. And this is the same structure you see here, again on the quartz, where you get a pair. So they've done it so very well. It's absolutely brilliantly rendered 12,000 years ago. Got to give it to them. And this is on the solar pattern from 2001, exactly the same structure that we can create pretty much every time. And by the way, if you get a reactor and you put it into a thing with X-rays after it's turned off, it produces these things on the X-ray film. So I'll leave it there, and I've probably got another 2 lots of that. So if I have to stop, You miss all the fun bits. Okay. I haven't even got to the important bits. What is it?
Non ci fa niente domande.
After we use okay. What is it?